Okay, welcome back. Now, let us first revise what we have gone so far. So, the goal of this topic, of what we have studied so far, is to understand the response of linear time invariant systems. The input to these systems is given one input process in a random process, capital X of t, and we are observing the response of this LTI system. In each case, we have first saw that whatever the response that has been generated due to the input is also a new random process y of t. It will have a mean value. It will have a expectation of the square of the process. It also has a autocorrelation function, etc. We have covered, that means we have covered all the temporal characteristics of the response or the output process capital Y of t. Now we come to the second phase where we want to study what are the spectral characteristics of such a process capital Y of t. So in fact we define what is called the power density spectrum. So in fact we know that a certain things already, that is, the input process is a random process that has a power density spectrum capital Sx of omega, and there is also a system called as linear time invariant system whose impulse response is h of t, or its frequency response is capital H of omega, sometimes called as the transfer function of the system. It is called as transfer function of the system. And we have a relationship between the input and the output. The response or the output frequency spectrum of the system is computed as the product of simply the multiplication of these two functions, the capital X of omega and H of omega. Okay, so whatever this result is coming because of due to linear time invariant system. For linear time invariant system, one can write the frequency spectrum of the response or the Fourier spectrum of the response, which is given as capital Y of omega, is equals to the input Fourier spectrum, that means the Fourier spectrum of the input signal times the transfer function of the system. Now this transfer function, as you know, it is unique to the system, whereas capital X of omega and capital Y of omega can be considered as random. Okay, now I'm going to use this result during the proof of finding the power density spectrum of the response of a LTI system, which is denoted as capital Sy of omega. Now we need to prove this relation, that this power density spectrum is equal to the input power density spectrum of the input signal times the square of the absolute value of the transfer function, or in some cases the square of the absolute of the transfer function can be called as the power transfer function. It's a power transfer function. Now that means the output, that is the PSD of the response, can be calculated as the product of the PSD of the input times the power transfer function. Okay. Now let us prove that one. It has got a very simple proof. Now we know that the PSD of a certain response of a output process capital Y of t can be found out by using this limiting expression. That means it is equal to the limiting value of as t tends to infinity of the expected product of the product of the Fourier transform of these two signals. Now I know what is here. Capital Y of omega is the Fourier spectrum of the output or the response. Capital Y of omega, as we saw, it is the output of a linear time invariant system. So I can use this relationship that we have studied earlier. I'm going to substitute that instead of Y of omega. I get the following. So here, so Y of omega will be equal to X of omega times H of omega, and its conjugate should be equal to the following. It should be the product of the individual conjugates of these two functions. That means the conjugate of Y of omega should be equal to the conjugate of the product. So nothing but equal to this. Now rearranging the terms and applying the expectation, that is the expectation operator, on the random variables capital X, I have this following result. The rest of the components can be taken outside the limiting expression. I have this following, and this is equal to nothing but this limiting value is nothing but it is the PSD of the input signal or the input process. It is a power spectral density of the input process. Therefore, I can write that as Sx of omega times the power transfer function, that is the square of the absolute or the magnitude of h of omega. Now this is the function that applies for all values, not just at only one omega, but it applies for all values of omega on the real axis. Okay, so we have proved the above theorem. Now using that, once we get the expression of the PSD, it is always very convenient for us to calculate what is the power of that output process. Now power of output of a process is calculated as this integration of the PSD function multiplied with a normalizing constant 1 divided by 2 pi. Now this is equal to, now if you substitute Sx instead of Sy, I substitute Sx times the power transfer function. Now the power can be calculated by using this closed form expression. That is, if you know the PSD of the input signal or the input process, then, and obviously the transfer function of the LTI system is known prior, then one can calculate what is the total power of the output process. Now there is the end of this topic of frequent spectral characteristics. Now I come to an important application of the concepts that we have studied earlier. So we take this example of what is called as a product device. So these product devices normally are very common in communications engineering. Now we see this in the case of whenever there is a input process that is multiplied with a carrier signal to generate a new process pi of t. Now the expression of this new process is pi of t is equal to the product of x of t times the carrier function or the carrier signal a naught cos omega naught t. Now if you see, observe this one, if this is this going to be a process, and what is the shape of this output process? Now if you look carefully, a naught is a constant, omega naught is a fixed constant. So this cosine is a single frequency carrier signal, and it is obviously varying with time. So whatever this x of t is multiplying near the amplitude of this cosine, so this is nothing but a new process that has the shape of a cosine but whose amplitudes are varying according to the values of the input signal. So there is a cosine, however there is a variation on this cosine fundamentally. So that is the kind of the process that we are looking at here. Now we want to prove here what will be the power density spectrum of this signal, this output signal, this new process that has been generated. So what is that going to be is given here, and we want to prove this expression. So what is this expression? Now observe what is on the right hand side. It is nothing but consisting of two copies of the input PSD, although each copy is shifted by omega naught units to the right side and omega naught units to the left side. So whatever the output power density spectrum is some modified version of the two copies of the input power density spectrum. So we're going to see that here. First, we're going to compute what is the autocorrelation function. The procedure is similar at what we have done earlier. So in order to obtain the power density spectrum, first we have to calculate the time averages of the autocorrelation function. Then we apply the inverse Fourier transform to obtain, we apply the forward Fourier transform to obtain the power density spectrum. So this is the same rule that applies again and again. Once again I repeat. So listen carefully. So how do we compute this power density spectrum of the output process? Capital Y of t is the following. That is, we first of all compute the time averages of the autocorrelation function of y. That means Ry of tau, t comma t plus tau. Then once we calculate the time averages of the autocorrelation function, afterwards we take the inverse of we take the forward Fourier transform of the time averages to obtain the power density spectrum. Okay, so first of all, the autocorrelation of the response or the output process is defined as the expected value of these two random variables of the process at times t and t plus tau. Now substituting y of t, we know what is y of t. Y of t is given to us as x of t times a naught cosine omega naught t. I am going to substitute that there. Now y of t plus tau is going to be y of t as t is equal to t plus tau. That means replacing t plus tau instead of t, I get the following expression. Now In this expression, the variables are, we have to identify what are the variables and what are the constant terms, what are non-random variables. Then if you see x is a random variable, the only random variable, and the rest of the terms are just ordinary variables or functions. Therefore, this expectation applies only to the random variables and the constants come outside. Now, if you recognize the expectation of here, it is nothing but the autocorrelation function of the input process. That is, should be equal to the autocorrelation function times a naught square, and this 1/2 is coming after writing this product of these cosines as a summation. Now, observing the first term in the summation, it is a term that is independent of time, and this is the term that is depending on time t. So, in the next step, we calculate the time averages of this autocorrelation function. Now, we also assume that the input process is Whitson stationary to make the matter simple. That means, look here, this autocorrelation function of the input can be replaced with Rx of tau. Now, the autocorrelation function of the output process should be equal to this expression here. Now, the time averages of the autocorrelation function of the output process is this following. It is the limiting value of this integral, average integral, taken average over time. Now, we know what is Ry of t comma t plus tau. Substituting that, I get this. Now, if you calculate these values, the second integral that is depending on time is a cosine, is the integral of a cosine that normally goes to 0. We have seen this in the earlier example. So, since that is equal to 0, we have only the first term equal to a naught square, the autocorrelation function of the input process, times cosine of omega naught tau. Okay. Now, once I have the time averages of the autocorrelation function, it is quite easy to calculate the power density spectrum. So, by Fourier transform properties, we know that. Okay, so we take the Fourier transform of the time averages to calculate the power density spectrum. Now, the Fourier transform of the right hand side of this expression should be computed now. So, we also note that the following result of the properties of the Fourier transform, that is, if x of t has a Fourier spectrum capital X of omega and another signal y of t has a Fourier transform y of omega, then the product of these two functions, is a third kind of a function. Now, the product of these two functions has a Fourier transform which is the convolution between, or convolution multiplication between the two Fourier transforms of the signal, or in fact that is equal to capital X of omega convolved with capital Y of omega. So, this means that a simple multiplication in the time domain converts to a convolution operation in the frequency domain. So, in fact, the power density spectrum or the Fourier transform of the time averages should now be equal to the convolution between the Fourier transform of x of the autocorrelation function is given as Sx convolved with the Fourier transform of the cosine of omega naught t tau. That should be equal to this following. The Okay, this whatever this expression I have written here, it is the Fourier transform of the cosine function, cosine omega naught tau. Now that is nothing but 1/2 and the sum of these two impulse functions at locations omega naught and omega naught, plus omega naught and minus omega naught. Now, by the properties of this convolution operator is a distributive operator. So it can be taken inside this summation. Now applying that convolution to the first term and applying the convolution to the second term, we get the following. Now the convolution of any function with the impulse function is the function itself. So we get, instead of this convolution for the first term, we get Sx of omega minus omega naught. That means this Sx at omega minus omega naught. Similarly, the convolution of this function with the second impulse function will lead you to Sx of omega plus omega naught. That means this omega plus omega naught comes directly and gets substituted into this PSD. So in fact, we have this expression here. This expression, if you study, is nothing but it is the sum of two copies of the power density spectrum of the input process. This one PSD is shifted by omega naught units to the right side, and the second copy is shifted by omega naught units to the left hand side. That means minus omega naught. Now, to have clearly see what is the form of this expression, I want you to take, for example, let the PSD of the input process be this following function, that is, which is given here. Now, the PSD of the output response should have two copies of this function, although they are shifted by omega naught, which are centered at omega naught and minus omega naught. You can see that here. And the amplitudes of these functions is not equal to the same as the original input, but it is multiplied with a naught square divided by 4. Now you can see that here, finally that is the expression. And okay, so this is actually the form of the output response. That means it will have two copies of the same spectrum of the input response, which are centered at omega naught and minus omega naught. Clear? Okay, thank you very much.